Hello maths fans! Dr. Tom Crawford here at the University of Oxford, and today we're looking at the maths of productivity. This is a very interesting piece of work which comes from Jaheim Archibald, the creator of Acumen, an app which helps you to maximize your productivity for a series of tasks. And let's be honest, who doesn't want to be more productive? We'll get to the details of the app later, but first, as usual, we start with the maths. We start by defining the productivity function. Let's call it P of t, where t here represents time. The idea being that your productivity for any given task will change depending on how long you've been working on that task. So based on our experience of doing tasks, we might in fact expect a curve that looks something like the following. So on the y-axis, we will do P of t. This can be time along the x-axis. So we will have an initial productivity, let's call it P0, and then it will take us some amount of time to sort of get to grips with what we're working on. And then we'll kind of reach a peak productivity. So this is kind of our peak productivity, or we might refer to it as a flow state because we are in the flow of the task. But then we possibly will maintain this for some amount of time. But as we continue to spend more and more time on the same task, we begin to get a little bit bored, a little bit tired, our energy levels begin to get lower. So we actually expect the productivity to decline, possibly asymptotically, into the future. Now this shape of curve is actually modeled really well by what we call a Poisson distribution or a Poisson function, which has the following equation. So P of t for a Poisson curve is an initial value P0 plus some amplitude A times t times e to the minus kt. So a function of this form for fixed constants P0, A and K will give you a curve that looks something like what I've drawn. And of course our goal is to try and work out what values P0, A and K will take and what they actually represent in the real world when we're thinking about productivity. Now, since we want to maximize the amount of time we spend in our flow state at peak productivity, it would feel like a good starting point to try and find the location of this peak. So we want to find the maximum of our function, our turning point or stationary point, which means we're going to need to differentiate the Poisson curve function. So if we now calculate dp by dt for this function, we're going to have to do a product rule because there are two time dependencies here. The P0 is a constant, so that just disappears. But then if we first hit the t, we're going to get a e to the minus kt, and then if I hit the exponential, that's then minus ka. I've still got the t, e to the minus kt. And for our stationary point for the location of our peak, we have to solve this equal to 0. So that's going to mean cancelling the a, we're going to lose the exponential because that is non-zero, and then we're left with 1 minus kt equals 0, so kt has to be 1, which tells us the time is going to be 1 over k. So this is going to be the location here of our maximum productivity, our flow state. It's going to occur at 1 over k, and we're going to call this phi. So the next question for our model is, what variables do we expect to determine the time taken to reach a flow state for a specific task? Again, if you think about your own experience, then it's going to depend on a whole host of factors. But there are two main factors that we're going to focus on. And those are going to be the effort that the task requires, which we will call E. So E is equal to the effort the task requires. And the second parameter is going to be beta, which is going to be the enjoyability of the task. So how much do we actually want to do it? Now, for simplicity, we can model phi, or 1 over k, as a linear function of these two variables. So let's suppose that phi, which is 1 over k, is simply equal to c1 times e plus c2 times beta, and then let's add in a third constant, c3. So this involves both of these key variables, the effort a task requires and the enjoyability of the task. Both of those, hopefully from your own experience, you can think about them and see how they would influence the time it would take you to get to your peak productivity or your flow state on a given task. And we're just going to model them as this simple linear function, and we'll explore that in a little more detail in just a moment. We're going to use the same two variables, e and beta, to also determine our initial productivity over here, given by P0. First, let's think about the enjoyability of a task. So if we are about to undertake a task which we find particularly enjoyable or very fun, then we would expect our initial productivity to be quite high because it's something we want to do, and so once we begin it, we're going to really want to get started and be quite productive in that first instance. And this is going to be exaggerated depending on whether we do or don't enjoy and therefore do or don't want to do the task. So we're going to say that P0, our initial productivity, is going to scale like beta squared. So clearly there is a positive correlation between initial productivity and enjoyment, and the squared term here is sort of exaggerating those feelings. And we're actually going to get a similar type behavior when we think about the effort. So for a low effort task, a task that we find quite easy, then you're going to be sort of at peak productivity quite near the beginning. So there might be like a slight adjustment time as you begin the task and get used to what you're doing. But if it's a low effort task, it's quite easy to just immediately get into the flow and get stuck into the task. And on the flip side, if it's quite a difficult task, you really have to think about it and you really have to get to grips with the task. So when there's a higher effort, you're going to be starting from a much lower level of initial productivity. So that's going to mean that we want to divide by E. It's going to have the opposite effect of the enjoyability. So when it requires a lot of effort, we expect initial productivity to go down. But similarly, we're going to square it and exaggerate that effect. So we're going to call this initial productivity, P0, is going to be equal to beta squared, the enjoyability squared, divided by the effort also squared. Now the final undetermined variable in our equation is the constant A, and this actually represents the amplitude of the peak. So as we increase the value of A, that's going to actually push this peak higher and higher. So if you think about this for yourself, when you're completing a task, is your peak productivity higher or lower when the task is enjoyable? So if you enjoy doing the task, is your peak productivity higher or lower? Hopefully, you will agree with myself and Jahim, who modeled this, that it's usually higher. If you enjoy the task, you tend to be more productive at that particular task. Now, the effort. What about a task that requires a great deal of effort for you to do it? So as we've just discussed, a high effort task might make your initial productivity a little bit lower, but once you get going, the potential of you in your flow state, and therefore the peak value, the amplitude, is actually likely, I think, to be higher when the task requires a lot of effort. So you can imagine almost, let's say, playing a video game, and for those video games which are really difficult and require a lot of effort and thought and concentration, when you're in the zone, you really are in the zone. So that's telling us that the high effort tasks actually will have a larger peak. You are more productive when you're in the zone, when you're in your flow state for those high effort tasks. So that means that our amplitude A, we expect to actually increase with beta, the enjoyability, and to increase with E, the effort. But those increases will not necessarily be linear, because in particular for the effort, if it becomes too high, then your productivity increase may actually be reduced. So as the effort goes up, we would expect the peak productivity perhaps to go up, but not quite as steeply as it did on a much lower effort task. So the rate of increase is slowing down. So what this all means, anyway, for the maths, is that a reasonable function for A in terms of beta and E is going to be A is equal to beta squared plus beta squared times the natural log of the effort. So this will increase with both enjoyability and effort, but for the effort in particular, that increase is going to tailor off if it becomes too difficult. Putting all of this together, we finally have our productivity function P of t as follows. P of t is equal to P naught, which is going to be beta squared divided by E squared, plus A, the amplitude given there, so that's going to be beta squared plus beta squared, the natural log of E, multiplied by t times e to the minus, and then we've got k. K we called over here 1 over k was equal to phi, and we said that phi was going to be this function. So that means k is 1 over that. So it's going to be e to the minus t divided by this linear function. So c1e plus c2 beta plus c3. So this function, P of t across the top of the board, is going to be our definition of the productivity curve. So now we have our mathematical formula, we need to make sense of the variables. So I've already mentioned what they all mean. We know that E is the effort of a task and beta is the enjoyability of a task. But remember, we also have these as yet undetermined constants, C1, C2, and C3, and they in fact are actually going to be user dependent. So they will be personalized for you as an individual because, of course, as individual humans, we all have different ways of getting into the zone and therefore different shapes to our productivity curves. So that's what C1, C2, and C3 are going to represent, and we will look at how they are derived in just a moment. But first, we're going to focus on E and beta. For any given task, you will first need to score that task by your own personal preferences as to what you think the effort that task requires will be and how much you enjoy that particular task. And again, these are going to vary depending on your mood on a particular day, or perhaps as you become better or worse at certain tasks. You may enjoy them more or find them to take up more effort or less effort. So you have to, for each task, score E and beta. Now, as humans, we like to score things out of 10. So that's basically what we're going to do. You have to score for any task your effort out of 10 and the enjoyability out of 10. However, when you plug in values for E and beta into our productivity function up here, you're going to get different shaped curves. And in order to maintain the shape that we are expecting, because remember, this was kind of our intuitive understanding of what a productivity curve should look like. So in order to maintain this kind of shape, it turns out that you actually need a specific range of values for your effort and your enjoyability. So you rank them out of 10, but then they're actually scaled so that E is between 1 and 5 and beta is between 1 and 2. And the way you do this is with the following formula. So our variables E and beta are scored out of 10 by you as the user, and then they are scaled to give a value of E, which is between 1 and 5, and a value of beta, which is between 1 and 2. And again, this range of values is just to ensure that our productivity curve has the shape that our intuition tells us it should have. Now, what about the user-defined constants, C1, C2, and C3? Well, these actually came into the model when we were talking about the location of the peak productivity or the flow state. So in order to determine these, you actually have to do experiments and measure as an individual user how long it takes you to get to what you would refer to as your flow state, to get into the zone when you are doing a particular task. So you have to collect a lot of data on a range of different tasks which each have scores for E and beta, the effort and the enjoyability across a range of values, because these constants are going to be the same for you as a user no matter the task that you are undertaking. But once you have this data, you have a series of data points, then we can actually use the method of least squares approximation to find the plane C1, C2, C3 which best fits the data. Suppose we have n data points for a series of tasks where you have measured your productivity and how long it takes you to get into the zone. Then we're considering the following function. We look at D, which is a function of C1, C2, and C3, and we want to consider the sum over those n tasks of the data point, let's call it phi I, minus the time that we're trying to work out, which is this 1 over k term, so that's C1 EI for your data point, plus C2 beta I plus C3. And we want to look at the difference between the function and the particular data that we have. And then, as with usual least square regression models, we're actually, subtracting those, we're actually going to then square the distance. Now, for those of you with a statistics background or who have studied a statistics module at university, then this may be familiar because this is simply a maximum likelihood estimator, which means that in order to find C1 and C2, C3 to minimize this sum of squares, then what we actually want to do is differentiate our function d with respect to the three variables. And just as we did when finding the location of our peak productivity, the turning point, we then actually solve that system of three partial differential equations all equal to 0. So the first one will be, we want to differentiate with respect to C1. Now the sum here actually doesn't really do much, so we can kind of ignore it as long as we're careful at the end. But for the differentiation at least, we can sort of pretend it isn't there and say, well, I've got something in a bracket, my C1 is like trapped within the square. So the 2 is going to come down. Then I've got the sum, which I'll just write, but we don't really worry about it. Then I'm left with my bracket now to the power 1. And then, of course, we have to do a chain rule because I've differentiated with respect to C1, and that was multiplied by EI. So I have to bring down the EI at the end. So if we now put this equal to 0 and then tidy it up, what we've got, the 2 doesn't really matter, and then sort of taking the summation through, remembering that EI multiplies all 4 of those terms and splitting them up into 4 separate sums, we're actually going to get that we have to solve, taking that one across, we've got the sum of phi I EI, this one times this one, is then equal to all of these. So that's equal to, we're going to be, C1 can come outside the sum, and then we're left with an EI squared. So EI from here plus the additional one over there. Then we've got plus C2 times the sum of beta I EI. And then we're left with C3 times the sum of the EIs. So plus C3 times the sum of EI. So that is the first equation from solving our least squares regression estimator, differentiating it with respect to C1, solving it equal to 0. And we're going to do something very similar for the other two. So I'll try and do these a little bit more quickly. So we want 0 equals the derivative with respect to C2. It's going to be very, very similar, except now the chain rule, I'm going to get a beta I term that's going to come out. So I can maybe even jump ahead a step. I'll risk it because I know what the pattern's going to be. It's going to be this, but with a beta I here. So I'm going to be left with the sum of phi I beta I is then equal to, I've got a C1 times the sum of EI beta I. I've got then a C2 times the sum of beta I squared, and then we've got the C3 times the sum of the beta i's. And then finally, if we do the 0 is equal to the partial derivative with respect to C3, what does that give us? Now when we do the chain rule, we do not get a term that comes out because C3 isn't multiplied by anything. So this time, we're just going to be left with the sum of phi I, nothing from the chain rule, is equal to then C1 times the sum of EI plus C2 times the sum of the beta i's plus the sum from 1 to n of C3. Now, of course, C3 doesn't depend on I, so you're just adding it to itself n times. So I could actually say this final term here is actually just equal to n lots of C3. So remembering that we're trying to solve for the constants C1, C2, and C3, and the beta I, EI, and phi I are all experimental data. They're things we've measured. Then we've actually got a matrix system. And we can rewrite this whole thing as we've got C1 times the sum of EI squared plus C2 times the sum of beta I EI plus C3 times the sum of the EI. So it's all of that times C1, C2, C3, and that has to be equal to the sum of the phi I times EI. And then that's the first row, that's our first equation. The second one, we've got here the sum of the phi I beta I, and the third one's going to be the sum of the phi I. And then going back to our second one, we've got C1 times the sum of EI beta I. C2 is multiplied by the sum of the beta I squareds. C3 is the sum of the beta i's. And then for the last one, we've got C1 times the sum of EI plus C2 times the sum of the beta i's, and then plus n lots of C3. So we have a matrix system here, 3 by 3 matrix, and now we just have to take this matrix, compute its inverse, and then we've got C1, C2, C3 equals inverse of this times this sort of product vector. So now we finally have all of the ingredients of our productivity function. It's based on a Poisson curve. We've included various log terms involving enjoyability and effort of a task. We've done this very neat bit of maximum likelihood estimation through a least squares regression model to find these user-dependent coefficients C1, C2, C3. And putting it all together, we now actually have a well-defined and fully understood productivity curve. So the question now is, how do you use this in practice? And this is where the Acumen app is going to help. Acumen uses the mathematical model that we've been discussing to create your own personalized schedule which maximizes your productivity. It's a problem we've all faced. You have several tasks to complete, and you kind of have to guess how long you think you can manage on each of them and plan your schedule accordingly. But that often means we spend too long on a particular task to the point where we become bored and unproductive, and it leaves us with the feeling of having wasted time. The Acumen app helps to solve this by generating a personalized productivity function for each user and creating a schedule to maximize the time you have available to complete your tasks. You can try it for yourself by simply clicking on the link in the video description and get started for free. You'll have access to your own personalized productivity calendar as well as reminders for upcoming deadlines. And if you want to take your productivity to a whole new level, then you can also sign up for a premium membership, which gives access to weekly reports, analytics, and can be integrated with both Google and Outlook calendars. By using the code on screen, you'll receive 40% off your first month's premium subscription. More information is available on the Acumen website. There are plenty of demos you can watch on the YouTube channel, and if you have any questions, then head over to the Discord. Links to all of these are in the video description. Now, back to the maths. So now we have a well-defined productivity function, P of t. We want to use this to actually help us to increase our own productivity. And the way to begin answering this question is actually to first define what we mean by total productivity. And in fact, we want to define productivity over a specified interval of time, which means we're going to use integration and the area under the productivity curve. So if we call this p bar, which will be a function of time, then this is equal to 1 divided by the length of the time interval, so t2 minus t1, and then we're going to integrate our productivity function between those two endpoints of the interval. So p of tau d tau. Now the easiest way to understand p bar is actually with an example. So let's pick some values for our parameters and look at the productivity for a specific task. So let's suppose that we take E, the effort of the task is 7. Let's suppose our enjoyability beta is going to be 3. And then of course we need our user-defined constants. So let's take C1 to be equal to 0.56. We'll take C2 to be equal to minus 0.24 and C3 to be equal to 0. Substituting these values into our general productivity function gives us P of t is equal to 0.11 plus 3.43 times t times e to the power of minus t divided by 1.75. So for this specific user with these user-defined constants, which will not change depending on the task, but for a specific task with effort 7 out of 10 and enjoyability, 3 out of 10. So something that's high effort that we don't really want to do because we don't enjoy it. We get this for our productivity function. Now, p bar is calculated over a specific time interval. So let's compare our productivity over 2 different time intervals for this particular task. So the first interval, let's suppose that T1, T2 is going to be the first 30 minutes. So that's 0 up to 0.5 in hours. First 30 minutes of this particular task. So we're not expecting to be hugely productive as it's something we don't really want to do. There's a lot of effort, so it probably will take us a while to get to our peak based on our earlier discussions. But nonetheless, we can compute p bar. And for this, I'll call it p1 bar. We're going to get a value here of 0.82. So just to clarify, what we're doing there is substituting in T2 to be 0.5, T1 is 0, so that gives us 1 over 0.5, so that gives us a factor of 2 in front of the integral, and then we integrate from 0 to 0.5 this function here. So of course this is done numerically, which is why I haven't written the whole thing out. So we're going to integrate that, and we're going to get an answer there of 0.82. Now, take the same task, but let's suppose that we are now instead 8 hours into it. So if we were still a 30-minute interval, but now we've spent 8 hours doing the task, we're probably a bit weary, a bit tired, a bit fed up. So we're kind of somewhere right down here on our productivity curve. So initially we were kind of here, and now we're kind of somewhere down here, let's say. Same length of time, substituting it in, we still get 8.5 minus 8 gives me 0.5, so we still get a factor of 2, but now we're integrating the function, the area under the curve, at a much later time. Now, before I give you the numerical answer, think about this for yourself. Do you expect your productivity for a task that you don't enjoy and takes a lot of effort, do you think you'll be more productive in those first 30 minutes? So even though it's going to be quite hard, you've got to get to grips with it, but those first 30 minutes, or will you be more productive having done it for 8 hours, potentially now being a little bored and a little tired? Well, based on the model, substituting in all those values, we get that P2 bar is actually much lower. It's 0.37. So we are less than half as productive 8 hours into the task than we were in those first 30 minutes. Now, if you go back to the picture, I've taken the first 30 minutes and somewhere quite far down the curve. And it turns out that the first 30 are better than somewhere quite far down. Again, this could vary depending on the task. That's important to remember. But for this particular task, we're better in those first 30 minutes. But we could, of course, be even more productive. So there's a couple of questions you can ask. The first one might be to say, well, if I'm going to pick any 30-minute interval, I'm probably going to want to pick the one over here, because this would give me the largest area under my curve where the width of the interval is 30 minutes. So this is the most productive 30 minutes I could find. However, we can't decide to jump in to the middle of a task. And this is kind of the key aspect of this entire calculation, this entire model. We have to actually start at 0. So whilst this 30 minutes will be the most productive, we in fact want to ever so slightly modify our definition of productivity. So what we want to consider, which I'm going to call P bar star, we want to consider our productivity as 1 over the amount of time spent on the task, because we have to start at 0. If we're going to use this in practice, we have to begin at 0 and go all the way up to some point. And the question is, at what point do we stop before our productivity falls so much, it's not worth continuing with the task. So we're going to start at 0, so t1 in this model is always 0. So it's going to be 1 over t, the integral from 0 to t of p of tau d tau. So it's still the same function, but for the purposes of maximizing our productivity, we just have to add in this more realistic concept that we have to start at 0, because that's when we start the task. So for practical purposes, this is what we want to maximize. And so therefore, we maximize this by differentiating and solving it equal to 0. So maximize p bar star of t by solving d by dt of it equal to 0. Now this calculation will almost certainly have to be done numerically, and that is certainly true here because we're going to substitute in our productivity function for this particular task and particular user, sub that into here, maximize it by differentiating and solving it equal to 0. So that's going to be done numerically. And then you get an answer for this particular task of t is equal to 3.16. Now, what that means practically is that for this particular task, where your effort is 7 and your enjoyability is 3, you want to spend 3.16 hours on that task, which is basically 3 hours and 10 minutes. So if you, as this particular user with these constants, wanted to undertake this task, the productivity model would tell you you should spend 3 hours and 10 minutes to maximize the amount of effort you're putting in versus the productivity and therefore the output that you get for that effort. So that's how we maximize productivity for a single task. However, you may be wondering, what do we do if we have several tasks? Well, the same theory applies. For each task, the user-defined constants will not change, but the effort and enjoyability will. So you modify those, you substitute everything back to get your new productivity function for that second or third or fourth task, and you work out the maximum amount of time or the perfect amount of time you should spend on that in order to maximize your productivity, which here means maximizing the area underneath your curve. Now, in theory, that works. However, and I'm sure some of you have already realized this, in practice, we don't have an unlimited amount of time to spend on all of these tasks. So here we can see that 3 hours and 10 minutes might be perfect for this task, but if you have 5 tasks you want to work on in a single day, and you only have 4 hours to do them all in, you probably can't spend 3 hours and 10 minutes just on one of them. Even though that would maximize the productivity of that one task, you have to equate them all against one another. However, we do have a mathematical tool which allows us to maximize a series of different functions under certain constraints. And again, I'm sure lots of you already know this, but what we're looking for here are Lagrange multipliers. If we have n tasks to complete, then the full system would look something like this, which can be solved numerically under the constraint of the total time available to spend on those n tasks. The final system of nonlinear equations, which can be solved also numerically, are those shown on screen now. Right, that's enough of the theory. Let's see this in action. Suppose you have 4 tasks that you want to complete in a day and 6 hours in which to do them. So, task 1. We are going to write an essay. Task 2, what should we do? Let's do some maths. We'll do some maths homework, maths problems. Let's sticking with the theme of things I do on a daily basis, task 3 is edit a video. And given my recent videos of exploring physics, let's suppose task 4 is studying for a physics exam. Studying physics. Okay. Now, in order to determine the productivity function for each of these tasks, we of course need to know the effort and the enjoyability, and we need to know the user-defined constants. So we're going to stick with these user-defined constants. So C1, C2, and C3 are as given over here. However, the effort and enjoyability is going to vary for these different tasks. So with the parameter values specified for the effort and enjoyability of our 4 tasks, essay, maths, video, physics, alongside the user-defined coefficients given here, we can compute the optimal amount of time to spend on each task, which is going to maximize our total productivity, where what we're doing is trying to get the largest possible value for the area under those individual productivity curves. So, crunching the numbers, we get task 1, essay. We are supposed to spend 42 minutes. Task 2, the maths. We are supposed to spend 1 hour and 50 minutes. Task 3, video editing. We are supposed to spend 1 hour and 7 minutes, which leaves the final 2 hours and 21 minutes to be spent studying physics. So this is the optimal solution, and this gives a productivity value of 6.13. So P bar star, as I'm calling it, is 6.13. Now, let's suppose I didn't have access to this beautiful model for productivity and the maths of productivity that we've just been discussing. Let's suppose instead I had just chosen some arbitrary values that to me felt like a reasonable amount of time to spend on these tasks. And given in particular I'm doing task 1 first, I'm going to start with the essay. Let's suppose instead I had spent 2.5 hours on the essay, so 2 hours and 30. Let's suppose instead I had spent 2 hours on the maths, so about the same as what I'm supposed to. 0.5 hours, so only 30 minutes on the video because I ran out of time, and then I squeezed in a final hour on the physics. So let's suppose the numbers given in that box. This is what I may have otherwise done if I had not mathematically studied how to be productive. So for these set of values, I get an alternative value of P bar star, which is going to be 5.16. So, what does this all mean? Well, if I had just followed my intuition and allocated what felt like the right amount of time to these various tasks, I would have had a total productivity of 5.16. But by using the maths of productivity and using the productivity curve, I've been able to increase that to 6.13. So that gives an almost 20% increase in my level of productivity across this 6-hour period. Now, I for one know that I would love to be 20% more productive, and I'm assuming all of you watching this would also like to be 20% more productive. So the key to it all is using maths, is using calculus, using this productivity function to help yourself be as productive as possible. Thank you everyone for watching, and thank you to Acumen for supporting today's video. Be sure to head over to their website to find out more about the maths of productivity and to join the Discord if you have any questions. And finally, please do remember to subscribe to my channel if you've enjoyed this and would like to see more maths-based videos. I'll see you soon. Take care.